4, and this module we're going to begin talking about how clouds form and even more importantly how air is able to rise in the atmosphere. Now before we begin, let me just give you one word of warning. This is by far the most complicated topic in this course. So make sure as you go into this that you plan a little bit of extra time to really understand this material. Alright, with that said, let's jump in. So our goals for this module are, first off, to understand how air cools as it rises. We already know that as air rises, it cools. Know the difference between a stable atmosphere and an unstable atmosphere. Then to know a little bit about cloud droplets, how they form, how they're able to grow, and then distinguish the types of precipitation and how we measure them. That said, let's jump into this first topic, which covers what's called adiabatic cooling. Now, that word adiabatic sounds pretty fancy, and it is, but as we delve into this material, you'll really get a better understanding of what it means. With that said, there are a few key terms that you need to understand when talking about adiabatic cooling. And the terms are, first, air parcels, which we've kind of already talked about. The word adiabatic itself, which we will talk about, and then what are called lapse rates. And we'll talk about those in this lecture as well. Okay, now first let's talk about an air parcel. So I have in this slide a picture of a balloon over here, and when we talk about an air parcel's just like a balloon, except for it's a theoretical balloon. Now, we all know that the air outside is one continuous body of air, but meteorologists don't think of it that way. Instead of thinking of it as one gigantic continuous body, meteorologists treat the atmosphere as trillions and trillions and trillions of small theoretical bubbles of air called parcels. And this is important because when we talk about air rising and air sinking, we're talking about these parcels of air rising or sinking. Now, one of the things that's really important about these parcels of air is they're isolated from the rest of the atmosphere, meaning they don't have any connection, any link to the outside atmosphere. It's the parcel and the outside atmosphere. And as a result, these parcels don't exchange anything with the outside atmosphere. They don't exchange heat, they don't exchange moisture. And I call that the Las Vegas rule. Basically, whatever happens in the parcel stays in the parcel. Now, because of this, the parcel is completely isolated from the rest of the atmosphere. And what that means is that the outside atmosphere doesn't warm up the parcel and it doesn't cool the parcel. Instead, whatever warming or cooling happens to that air inside of the parcel is due to something going on inside of the parcel. So warming and cooling don't happen due to any process outside of the parcel. Now, there are many types of real-life air parcels in the atmosphere. Things like convective thermals, a hot bubble of rising air, or smoke. Obviously, that smoke is independent from the surrounding atmosphere, or particles of air pollution, and these are just a few things. Now, with this said, what happens to an air parcel as it rises? Well, if we have a parcel of air, so think about it like a balloon, and it rises in the atmosphere, pressure begins to decrease. As a result, the parcel begins to expand. Now, as it expands, energy has to be used to perform work on the parcel, allowing it to expand. That causes the parcel to cool. So basically, as the parcel rises, it expands and it cools. You don't need to understand this thermodynamically in terms of like the different equations and how work is done and so on. All you need to know is that as the parcel rises, it expands and it cools. And then the opposite is true too. As the parcel sinks, it contracts, it shrinks, and it warms. So it contracts and it warms. Now when we talk about adiabatic processes, those are actually what are cooling or heating the parcel. An adiabatic process is simply a process where the parcel of air does not exchange heat with the outside environment. So when you hear the word adiabatic, all that it really means is that that parcel of air is not exchanging any heat whatsoever with the outside. It's not receiving heat, it's not giving off heat. And so that's what an adiabatic process is. As a result, any heating or cooling that happens to the parcel isn't due to it receiving heat or giving off heat. It's due to one of two things. Either due to expansion or contraction. Expansion again cools the parcel, contraction again warms the parcel. Or the release of latent heat. Now, this one's a little bit trickier. Remember, inside a parcel or in our atmosphere, we have moisture. Well, every single air parcel also has moisture. As that parcel gets higher up and it expands and it cools, it gets closer and closer to the dew point temperature. Eventually, if the parcel cools to the dew point temperature, it becomes saturated. As a result, moisture condenses and latent heat is released. Now, this is still an adiabatic process, at least for the purpose of this class. It's not receiving any heat from outside of the parcel. It's the moisture inside the parcel that's giving off the heat. So it's still an adiabatic process. Now, with all of this said, as an air parcel rises, it expands and it cools. But how quickly does it cool? What determines how fast it cools or how slow it cools? Well, it all has to do with if the parcel is saturated or not. That's what determines this whole thing. The parcel will cool at one rate if it's unsaturated. It'll cool dry adiabatically. On the other hand, if the air inside the parcel is saturated, there's latent heat being released inside the parcel. As a result, that slows down the rate of cooling. In this case, the parcel cools moist adiabatically. So, unsaturated parcel, dry adiabatically. Saturated parcel, moist adiabatically. Now let's talk about that real quick. The way the dry adiabatic process occurs is as air rises, it cools at a convenient rate. A convenient and known rate. And this is the rate that meteorologists use. And the rate is 10 degrees Celsius per every 1,000 meters. So if you have a parcel of air at the surface, and whatever temperature it is at the surface, and you allow it to rise 1,000 meters, it cools 10 degrees Celsius. So if it's 20 degrees Celsius at the surface, it's going to be 10 degrees at 1,000 meters. At another 1,000 meters, now it's 0 degrees, and so on. And so that's what this lapse rate is. The lapse rate is the rate of cooling with height. So here's an example here. We have an air parcel at the surface at 30 degrees Celsius. And we assume that it's unsaturated. As we push it up to 1,000 meters, it cools to a temperature of 20 degrees Celsius. Push it up another 1,000 meters to 2,000, and it cools to a temperature of 10 degrees Celsius. Now the opposite is true too. If we let the parcel sink 1,000 meters, instead of cooling by 10 degrees, it warms by 10 degrees. So if we have a parcel in the sky with a temperature of 10 degrees Celsius, and we push it down 1,000 meters, it cools to 20 degrees Celsius, it warms to 20 degrees Celsius, and so on. Now, there's a few different ways that you can calculate this whole cooling rate. The way I like to do it is using a very simple formula. And here's what the formula is. The temperature at the height you're looking for equals whatever the temperature was at the surface minus the lapse rate times the height. Minus the lapse rate times the height. Now, if you don't really like to do math and you don't like playing with formulas, another easy way to do it, going back to this image, is draw a parcel at the surface and keep raising it to your desired height. So then first raise it 1,000 meters, then 2,000 meters, then 3,000 meters, and so on. Now don't worry, I'm not going to give you a problem with what's the parcel at 100,000 meters, or what's the parcel at 50,000 meters. I might give you as high as 10,000 meters, but in that case you're only going up 10 levels. But if you want a shortcut, this formula is the shortcut. We can actually do an example using this formula. So we have a parcel of air with a temperature of 40 degrees Celsius at the surface, and we release it into the atmosphere. And it's unsaturated. What will its temperature be at 4,000 meters? Well, to find that out, we just plug our numbers into the previous formula. The temperature at 4,000 meters equals the temperature at the surface minus the lapse rate, 10 degrees Celsius per 1,000 meters, times 4,000 meters. Once we do that, we get something that looks like this. The temperature at the surface is 40 degrees Celsius. That was from up here. 10 divided by 1,000 times 4,000 is just 40 degrees Celsius. And so we just get 40 minus 40, which equals 0. And that is our temperature at 4,000 meters. But again, if you're not comfortable doing that, just start with a parcel at the surface, 40 degrees Celsius. Raise it to 1,000 meters. Now it's 30 degrees Celsius. 2,000 meters, now it's 20 degrees. 3,000 meters, now it's 10 degrees. 4,000 meters, now it's 0. So just every 1,000 meters you go up, you take 10 away. You take 10 degrees Celsius away. All right? Now, that was for an unsaturated parcel. But what about a saturated parcel? In this case, a parcel that's saturated is a parcel that is cooled to the dew point temperature. Now remember, the dew point temperature is the temperature that air needs to be cooled to in order for saturation to occur. It tells us how much water vapor is in the air. If the dew point temperature is 10 degrees Celsius, then the air needs to be cooled to 10 degrees Celsius. If the dew point temperature is minus 10 degrees Celsius, then the air needs to be cooled to minus 10 degrees Celsius, and so on. Just like heat, let's assume that whatever's in the parcel stays in the parcel until it condenses. We'll worry about that more later though. For now, just whatever's in the parcel stays in the parcel. Now, as a parcel of air rises, the dew point really doesn't change much. Why? Because moisture isn't leaving the parcel. Moisture isn't really leaving the parcel, so the dew point temperature really doesn't change much. Now, with that said, because of decreasing pressure, the dew point temperature actually does drop 2 degrees Celsius per every 1,000 meters. You'll look at that in this week's activity, but I just want you to keep that in the back of your head. Because moisture doesn't leave the parcel, the amount of moisture in the parcel doesn't change. With that said, if a parcel of air cools to the dew point temperature, moisture begins to condense. As moisture condenses, clouds form, and latent heat is released into the parcel. This latent heat doesn't quite warm the parcel up, but it slows down the parcel's rate of cooling. In this case, the parcel now rises moist adiabatically, and its rate of cooling, that lapse rate, is now 6 degrees Celsius per every 1,000 meters. So instead of cooling at a rate of 10 degrees Celsius per every 1,000 meters, it cools at a rate of 6 degrees per every 1,000 meters. Now, here's a set of examples that you can do at home, and you could either use that formula, or you could draw a picture or showing you how to do it. I'll give you a few of the answers right now, but take a moment, pause this video, and try these. With that said, this first case, the parcel is unsaturated, meaning it cools at the dry adiabatic lapse rate. This case down here, it is saturated. It cools at the moist adiabatic lapse rate. So up here, it cools at a rate of 10 degrees Celsius, per every 1,000 meters. So you can tell my penmanship on the computer isn't the greatest. That's okay. Down here, it's minus 6 degrees Celsius per every 1,000 meters. All right, so up here, again, dry adiabatic, down here, moist adiabatic. Now, to determine the temperature of a parcel, we use this equation here, where change in temperature equals elevation times lapse rate. And here's an example of if the parcel rises dry adiabatically. But again, you can do this for each one of these cases. And that's the conclusion of this lecture. Just a quick review. The atmosphere is split up into trillions and trillions of tiny air parcels. Each one of those air parcels rises and cools at a rate independent from the surrounding atmosphere. This is called adiabatic cooling, and it cools at a temperature or at a rate of 10 degrees Celsius per every 1,000 meters if it's dry, 6 degrees per every 1,000 meters if it's moist. Now in the next lecture, we're going to talk about why we even care about this. We're going to get into the topic of atmospheric stability. Until then, I'm Terrence Mullins. Thank you for watching.